We are moving on to how we find zeros in yet another way, and that way is using the quadratic formula. If you are a sophomore, junior, definitely senior, you know the quadratic formula, or at least you should know the quadratic formula by this point. I am not a huge lover of the quadratic formula, mostly because there are a lot of places that students can go wrong. There's a lot of places that students can make careless mistakes. There's squares and square roots and pluses and minuses and numerators and denominators. There's a lot of moving parts to it, and very frequently students will mess one little thing up and everything else after that point will be, ruined. So if you can avoid using the quadratic formula, it probably would be a good idea. Having said that, on the SAT, this note is over here, by the way, we have seen several questions that will ask you for the solutions, the zeros, to a quadratic equation, and then the answer choices will look like the quadratic formula. We'll write the quadratic formula down in a moment here, but you might see an answer, that looks like this, or you might see that the solutions are 1 plus root 2 or 1 minus root 2. Whenever you see answer choices that look like they are formed from using the quadratic formula, you most likely are going to have to use the quadratic formula. There is often no other way or no other really efficient way to do some of these questions. So if you want to write the quadratic formula down on your own, go to it. I'm going to write it right now. One of the ways that if we have, let me step back here for a moment. If we have a quadratic equation, ax squared plus bx plus c equals 0, and we want to find the values of x that satisfy this equation, which again are the roots or the zeros or the x-intercepts, we can use x equals negative b plus or minus, I'm not going to sing the song, some of you may know, plus or minus b squared minus 4ac all over 2a. So whatever your A, your B, and your C are, they are going in for A, for B, and for C. And whatever values you get out of this formula are the values of x that will satisfy this equation. Let's start with a reasonably simple example. Example 13 at the bottom of the page. Do remember that in order to use the quadratic formula, you need to make sure you get your quadratic into pure quadratic equation standard form first. So we need the solutions to x squared plus 1 equals 6x. First things first, we've got to take that 6x, which will become the bx term, over to the left-hand side by subtracting it from both sides of the equation. So we get x squared minus 6x plus 1 equals 0. I always like to write down my a, my b, and my c values before I start trying to plug anything into the quadratic formula, just so it's very nice and visual and simple. Now it's just sort of a substitution issue. So I have x equals negative b, which is going to be negative 6, plus or minus the square root of b squared minus 4a and c. Again, I'm just punching in the numbers where they're supposed to go, over to a. So now cleaning up a bit, negative 6 obviously is 6, plus or minus, what's all this going to be? It's going to be 36 minus 4 all over 2. Moving down here a little bit, I'm going to get 6 plus or minus the square root of 32 all over 2. I'm actually going to now, I'm going to split that denominator so that it is over each of my parts here. So now moving up here, I've got 3 plus or minus. Breaking down this square root of 32, there's multiple ways to do that. Most of you should be familiar with how to break down that square root. We do cover that in a different section. I'm going to do it using the largest perfect square that goes into 32, which is 16. So I can break 32 down into 16 times 2. That root 16 times 2 can be broken into root 16 times root 2, and of course root 16 is 4, so I'm going to do 3, that was the 6 over 2, plus or minus 4 root 2 over 2, and there is one more bit of cleaning up I can do here because I can cancel the 4 and the 2 and get a 2 up here. So I just get 3 plus or minus 2 root 2. Those two values of x, 3 plus 2 root 2 and 3 minus 2 root 2, are the two values of x that will satisfy this quadratic equation. So 3 plus or minus 2 root 2. Again, if you were to see answers that look like 3 plus or minus 2 root 2 to a question that asks you for the solutions to a quadratic equation, most likely the quadratic formula is the way to go. At the top of the next page, we have to talk about one little but very important piece of the quadratic formula, that piece being known as the discriminant, which is, I'll highlight all of this here, the stuff under the square root, the b squared minus 4ac. A few pages ago, we talked about the fact that parabolas can cross the x-axis 2 times. They can just touch the x-axis. In other words, they can be tangent to the x-axis. They can also not touch the x-axis at all. And whether or not the parabola touches, or how many times the parabola touches the x-axis, will correspond to how many real zeros the parabola has. This is 2 real zeros, this is 1 real zero, and then over here on the right we have no real zeros but 2 imaginary. All quadratics do have 2 roots or 2 solutions, so if you have no real, you must have 2 imaginary. Well, the discriminant itself will tell us which of these 3 scenarios we are dealing with, and there have been a couple of questions on which you didn't really need to go any farther than that. In other words, you didn't really need the roots. You just needed to know what type of parabola you were dealing with, whether it touches twice, once, or no time. So in example 14, what we are going to do is we are going to determine the value of the discriminant for each of these 3 functions, f, g, and h. So for function f, I'm going to go ahead and list a equals b equals c equals. I will always do that whenever I'm using the quadratic formula or dealing with discriminants so that I don't mess anything up. A, of course, the coefficient in front of the x squared term is 1, b is -2, and c is -1. So now plugging those numbers into the appropriate places in the discriminant, I get -2 squared minus 4ac. And I'm not going to do this in my calculator. You can use your calculator here if you want to, but -2 squared is +4. We're going to be adding 4. That's -4 times -1, which is +4. The 1 is kind of irrelevant here. -4 times -1 is +4. So we're getting a +8 for our discriminant. We have a positive discriminant. Let's move on to function g. We have a equaling 2, b equaling -16, c equaling 32. There I definitely do want to use my calculator. -16 squared is 256, but I don't want to run the risk of making any careless mistakes here. So let's do -4a and c, and let's go right into the calculator, and let's do -16, and we are squaring that, and we are subtracting 4 times 2, times 2 times 32, and enter, and that works out nicely to 0. So we got a 0 discriminant for function g, for quadratic g. For function h, we have a equals 1, b equals 6, c equals 12, and we are doing b squared minus 4ac, and here we're going to get 36, 4 times 12, 48. So we're going to get something negative. I believe it's -12. I hope it's -12. Again, I should be checking this in the calculator since I'm allowed to, but all I really need to know as of this point is that I'm getting a negative discriminant there. So in this table, we are going to bring everything together. We're going to look at the discriminant and what is happening in the quadratic formula. The discriminants are in bold here. I'll actually go ahead and highlight. I'm going to do this in 3 different colors. If you don't have 3 different colors, that's perfectly fine, just to make it easier for you to see what's going on here. So across the top of this table, I would like to write down positive discriminant, so b squared minus 4ac is greater than 0, a negative negative discriminant. No, that's not negative. Don't write that. I apologize. That's my fault. This is a 0 discriminant, so that's b squared minus 4ac equals 0. And over here on the right, we have a negative discriminant. That's b squared minus 4ac is less than 0. So in the case of the positive discriminant, the case of function f, and by the way, these are the three functions that we used in the previous example, f, g, and h, where we got a positive 0 and negative discriminant. So we can see, we'll zoom in on this step here, where we have the 2 plus root 8. We're taking the square root of a positive number. Well, the square root of a positive number is a real number. It might not be a rational number. It might not be a nice, neat number. Of course, if you had something like 2 plus or minus root 9 over 2, then you're going to have 2 plus or minus 3 over 2, which is 5 over 2 and negative 1 over 2. If the number under the square root is a perfect square, you're going to have a really nice, neat, rational root or 0. But even if you don't have a perfect square, in the case of 8 is not a perfect square, you're still going to get a real solution. Even if it's a little bit ugly, you can see the final zeros are down here, the simplified zeros. You are still going to get a real number here, which means you're going to get 2 plus that real number over 2 and 2 minus that real number over 2, which means, again, you will end up with 2 real solutions. And as I said at the top of the page, 2 real solutions also means that the parabola is going to hit the x-axis at 2 points. 2 points on the x-axis. Each of those is a real root or real 0. And so we can sort of see how it all comes together here. Again, when we have a positive discriminant, we are going to end up with 2 real solutions. The quadratic will have 2 real roots or zeros, and the parabola that corresponds to the quadratic will have 2, we're going to write 2 down there at the bottom, 2 x-intercepts. In the case of the 0 discriminant, well, remember, we'll home in on this step right here, 16 plus or minus root 0. Well, root 0 is just 0, and 16 plus 0 and 16 minus 0, well, those are both 16. So we're just ending up with 16 over 4 here, which of course only equals 4. So we have 1 real root or 0 in this case, and when we only have 1 real root or 0, we have a parabola that has only one x-intercept. So again, when the discriminant is 0, we're going to end up with 1 real root or 0, and we are going to end up with a parabola that kisses or is tangent to the x-axis. When the discriminant is negative, as it is for function h over here, again, if you look at this spot right here, we've got that negative 12 discriminant. Well, remember, that means that we're doing 6 plus or minus some imaginary number, not I itself, but some imaginary number there, because the square root of a negative is always imaginary. So what we're going to end up with here are 2 roots where there is an imaginary number in this position over here. Simplified, we get to 3 plus or minus I root 3. That is 2 imaginary or complex solutions. The parabola will not touch the x-axis at all, and will have 0 x-intercepts. So we can see from this table that I'd say the 3 major things here are knowing what type of discriminant we have. I shouldn't be doing this in green because I have already used, wow, that got messy. I've already used some green here. I probably should have used, let's just use pink. So we've got a positive discriminant. Let's see if I can get rid of this. Ooh, that wasn't bad. We've got a positive discriminant. The positive discriminant means 2 real roots or zeros, and that means 2 x-intercepts. When we have a 0 discriminant, that means we're going to have 1 real root or 0, and we are going to have 1 intercept, 1 x-intercept. And then when we have a negative discriminant, we have no real roots or zeros. We have 2 imaginary complex zeros. We have a parabola that does not touch the x-axis at all. We have 0 x-intercepts. If you are going for an extremely high score, let's say well into the 700s, you are going to want to know this information. And I hesitate to say memorize it, because I always would like my students to understand what's going on. And if you look at this table and review it a few times, you should understand what's going on here. But I would say that this stuff eventually, after you understand it, should really just be committed to memory. There have been a couple of questions that have shown up on the test where your only, or certainly your best option was to use your knowledge of the discriminant to solve the question. By the way, the root in the middle, this one real root, we call that a double root. It has a multiplicity of 2. We talked earlier about the fact that parabolas that hit the x-axis can always be written in this one factor, like this x minus 1, 1 factor squared. So we would say that the root or the factor has a multiplicity of 2. Roots can have even or odd multiplicity. Of course, this one has even multiplicity. This equation right here is just another form of the g of x function that we have in this table. We've just converted this to factored form, or you could also call this vertex form, I suppose. So we will talk in another section about multiplicity and what multiplicity means for x-intercepts and how functions look and all that stuff. At the top of the next page, we are going to take a look at an example of a question on which using what we just learned about the discriminant will almost certainly be the fastest and easiest way to proceed. So in example 15 here, if you want to try this question on your own, if you think you understand the discriminant information well enough to do this on your own, obviously pause the video and then come back and join us once you're done, or if you get stuck. In example 15, we have if the graph of some quadratic function intersects the x-axis at only one point, what must be the value of a? What must be the value of a? Value of a is what they're asking. The key here is recognizing this phrase right here. I guess it's that whole phrase. Or even this whole phrase. Let's keep adding words. Intersects the x-axis at only one point. That is a giveaway that the discriminant may play a role in most easily answering this question, because remember, when the graph intersects the x-axis at only one point, we know that b squared minus 4ac must equal 0. It is the b squared minus 4ac equaling 0 that produces the intersection at only one point. Remember, intersecting at only one point is when the parabola is tangent to, that's if it opens downwards, here's if it opens upwards, is tangent to the x-axis, just kisses the x-axis and then goes along its merry way. So what I can do on this question, since I know what b is, in fact, I'm going to list my values here. A is just a, that's the one I don't know. B is -12 and C is 9. Since I know B and C, and the only thing I don't know is A, if I start plugging my values for B and C into this equation, I'll be left with an equation with only one variable, which means this will all turn into very simple algebra. So what we're going to do is b squared, which is -12 squared, minus 4a is just a. I don't know what a is, so I'm just going to leave a as an a. C is 9. So -12 squared. I can use my calculator here, and as always, I probably should, but I do know that the square of 12 is 144, minus 4 times 9 is 36, so that's 36a. Remember, that all has to equal 0, so this is 144 minus 36a equals 0. Just rewriting that there, plus 36a plus 36a. I get 144 equals 36a. 144 divided by 36 should be 4, but that is a calculation I'm going to check in the calculator. 144 divided by 36, and yes, it is 4. So a equals 4. That is what they were asking me for, and I am done. So I've just used the fact that the discriminant must equal 0 when a parabola intersects the x-axis at only one point in order to turn this question into a very basic algebra question. Now, some of you might recognize, those of you who are quite proficient with quadratics, you might recognize that this is one of those cases where, remember when a parabola touches, we actually discussed this a few pages ago, that when a parabola just touches the axis, the quadratic is always going to have the form where you have just one factor squared. So some of you might have been able to figure out that this standard form quadratic is going to have to factor into something with negative 3's at the end. That's to produce that positive 9 and this negative middle term. And you might also, through various ways, be able to determine that the factor that you are squaring must be 2x minus 3, because when you FOIL this out, 2x times 2x is 4x squared. Then you're going to get a minus 6x minus another 6x, right? 2x times negative 3, negative 6x. Negative 3 times 2x, another negative 6x. You will get negative 12x. And then, of course, last terms will be plus 9. So when you FOIL out 2x minus 3 squared, you do indeed get back what we have here. And in doing so, you can see that your A needs to be 4. So the point is that there are other ways to do this question. You don't have to use the discriminant, but the discriminant certainly is, in my opinion, the most efficient way to go here. And as I've said a couple times, I believe I said it on the previous page, there are some questions where the discriminant will pretty much be the only way you're going to want to go. Almost always multiple resources on every SAT question, but the discriminant certainly comes in handy on some quadratics questions. I would suggest knowing the information about the discriminant well.